In this video, we're going to prove our other theorem about powers of group elements. This time we're going to deal with the case in which A has finite order. So we're going to assume throughout the video that A is an element of G, a group, and the order of A is a finite number, which we will call n. So n is a positive integer. Okay. So we're going to prove the following theorem. Let's let G be a group, and A an element of G, such that the order of A is n, where n is a positive integer. Okay, then, I think we're calling this theorem 2. I think the one in the last video is theorem 1. Anyway, then, for integers I and j, we have a to the I equals a to the j, if and only if. Okay, so we started out pretty much the same way we did with the previous theorem. The previous theorem said a to the I was equal to a to the j if and only if I and j were equal, if and only if the exponents were exactly the same. This time it's a little bit different. This time the condition is if and only if I is congruent to j mod n. Alright, so before we even get into the proof, let's just set the stage here and talk about why we should even believe something like this would be true. So why would it be that a to the I equals a to the j if and only if I and j are congruent mod n? Well, let's take an example. Let's suppose that the order of A is, I don't know, 5, just picking a number here. Alright, so then what would we expect to see happen if we wrote down a whole bunch of entries in this list of powers of A? And I'm going to write down a whole bunch of them so we have quite a bit to talk about here. Okay, so I could start counting out these elements, counting out powers of a to the 0, which is, of course, the identity, and then a to the first, which is a, and then a squared is a times a, and so on. I'm not going to write out all of these, but then when we get to a to the 5th, we get the identity again. And then what happens when we get to a to the 6th? Well, a to the 6th is just taking the previous entry in the list and multiplying it by a. Well, that should take us back to a. And then multiplying by a again should give us a times a, the same thing that a squared was. And then multiplying by a again, I'm multiplying by a each time, multiplying by a again should give me a cubed. So you'll notice I'm getting these pairs of elements here, and I'm going to try and color code these a little bit. So I have a to the 0 equals a to the 5th, and then different color, a to the 1st seems to be equal to a to the 6th, and then different color, a squared seems to be equal to a to the 7th, and then a to the 3rd equal to a to the 8th, and so on. And I guess if I kept going, I would find that a to the 4th is equal to a to the 9th. So I have this pattern where powers of A are congruent to each other, or rather they're equal to each other, if and only if their exponents are congruent mod 5. 1 to 6, 2 to 7, 3 to 8. If I kept going, a to the 10th would be the identity again, I think, because that's just a to the 5th squared, so that's the identity squared. And 10 belongs to that same congruence class of 5 and 0. And then a to the 11th would be equal to a to the 1st again, and so on. So that's just a reason to believe that this theorem is likely to be true. But we want to prove it formally now so that we know that this will be true no matter what we pick the order of A to be, no matter how exactly the elements in the list work out. We can actually prove this so that this is firm for now and all time. So anyway, here's the proof. So again, this is a two-parter because it's an if and only if. So we'll start by proving what I think is probably going to be the easier one first. Now this time, by the way, I don't think there's really one part of the proof that is as straightforward as what we had last time, where we said, well, if I equals j, then a to the I has to equal a to the j. I think this time we're probably going to have to do at least a little bit of work each way. So let's start with this direction. So let's assume that I is congruent to j mod n. Okay, I want to show that a to the I equals a to the j as group elements. Now, one thing I do very often when I'm writing a proof, and I'm not quite sure how to start, is I just take this and I go ahead and unpack it. So when I say unpack, I say, what does it mean for this to be true? Well, this means that I plus k times n is equal to j for some integer k. That's what it means to be congruent mod n. So that's what I'm going to do. I'm going to go ahead and write that out as a statement in my proof. Since I is congruent to j mod n, there exists some k in integer such that I plus kn equals j. Now remember, n is the order of a, so that's the order, and then this is some multiple of it. Okay, so now keep in mind, k might be a positive integer, it could be a negative integer, it could be 0. We don't know a whole lot about it. But now, I'm going to use this to write down what a to the j is. A to the j is equal to a to the I plus kn. I'm going to add a little transition word there, so I'm not jumping into a calculation without saying something first. All right, so then I know that a to the j is equal to a to the I plus kn, and now I'm going to use my properties of exponents, props of exponents, to expand that a little bit further. So that's a to the I times a to the kn. And then I can further expand that by saying that's a to the I times, and now I'm going to do something a little bit nifty here. Because I know that a to the n is the identity because the order of a is n, I'm going to rewrite this as a to the n raised to the k. That should be an n there. That's a to the n raised to the k. All right, so all this is properties of exponents here. And then since the order of a is n, this is a to the I times just the identity to the k, since the order of a is n. But now look at this. What I have left after all that, the identity to any power is just the identity. So I have a to the I. Okay, so therefore, a to the I is equal to a to the j, because those are the two ends of this huge chain of equalities I put together here. A to the j, I simplified that, or rather complexified it, I guess, and then used properties of exponents to rewrite, and then realized that basically what was happening here was this part of the exponent referred to a power of a that just doesn't count for much. It's the identity. So now what I have left is a to the I, so that has to be equal to a to the j. So that's perfect. That's the first half of the proof there. That's exactly what I wanted to show. All right, so let's put a period on that. And I'll even say this concludes the first part, just because I like, a little victory dance after something successful. Okay, so now let's move over and give ourselves some room for the second part. So now here's the second part of the proof. So I think this is the rightward direction. Assume a to the I equals a to the j, where I and j are integers. And really, I should be doing that on each part. I think I forgot to introduce I and j on the previous part, but I really should do that. It's just good manners. We will show that I is congruent to j mod n. Okay, this part's going to be a little bit trickier, and I think this is probably going to be the part where we have to use the fact that n is the smallest positive integer exponent that takes a to the identity, but we'll see. Now, one thing you may recall from the previous proof was that a useful step for us at this point, if we knew that this was true, was to somehow relate this to some knowledge about the identity. Because any useful application we're going to make of the order of a here is going to require us to be able to talk about the identity. We need some power of a to equal the identity for us to be able to use this fact. So I'm going to start out the same way, or sort of the same way I did in the previous proof, which is I'm going to rewrite this equality here so that we have the identity on one side of the equation. So since a to the I is equal to a to the j, I can multiply on the left on both sides of the equation by a to the negative I. That's going to get rid of a to the I for me. So I have a to the negative I times a to the I equals a to the negative I times a to the j. And that leaves me with the identity on the left side, because this was a to the negative I plus I, that's a to the 0. I'm just going to put that in parentheses there, that's my work. And then the right side is just a to the negative I plus j. So I have the identity equals a to the j minus I, whatever that is. All right, now j minus I again could be positive, could be negative, could be 0. We don't know yet. All we're hoping to show is that that number, j minus I, is divisible by n, because that would tell us that I and j are congruent mod n. So I'm just going to put it over here in a note. I want to show that j minus I is divisible by n. But now, once I know that I want to do that, because my goal is to show that I is congruent to j mod n, once I know I want to do that, the thing that always leads me to is if I want to show something is divisible by n, one thing I can try is just divide it by n, get a quotient and a remainder, and see if I can prove the remainder is 0. So that's exactly what I'm going to use here. By the division algorithm, since n is a positive integer, there exists q and r integers such that j minus I is equal to nq plus r, and 0 is less than or equal to r is less than the thing that we are dividing by, which is n. All right, so just moving over a bit. Let's see. So let's go ahead and write that down. Let's use this in the above equation and see what we get. So then we have the identity equals a to the nq plus r, because that's the same as j minus I. But then I can again use properties of exponents. I get the identity equals a to the nq plus r equals a to the nq times a to the r, which is the same as a to the n all raised to the q times a to the r. But now look again. We know that a has order n, so this a to the n here is going to be the identity. So what I have there is just one big power of the identity, 1 to the q times a to the r. And any power of the identity is just the identity, so a to the r is all we have there. And in the meantime, the left side of that equation was 1, so now I know one equals a to the r. But now wait a minute. We know r is less than n, which is the order of a. So this should trouble us because we've got a power of a equal to the identity, and that power of a is using an exponent less than n. And you might think we have a contradiction here, but we actually don't. There is one alternative that allows this to be true without contradicting n being the order of a. You'll notice that when we set up r, the remainder of that division, r could be anything between 0 inclusive and less than n. So the option that actually exists is for r to be 0. If r were any positive integer less than n, this would contradict n being the order, because n is the first positive integer that we can exponentiate a to and get the identity. But we could have r equals 0, so that's exactly what we have to have. That's the only thing that would work here. Since n is the smallest integer, smallest positive integer, since that's true, we must have r equals 0. So that's equal sign, r equals 0. Okay, and because r equals 0, and remember r was in this equation over here that I'm circling in red, that means that j minus I has to be just nq. Well, if that's true, then I plus nq equals j by just algebra. But that means, wait a minute, that should be a very recognizable statement there. What does that mean? So by definition, I is congruent to j mod n, and that's exactly what we wanted to show. So I think we're done. I think that's the second part. So that means that a to the I equals a to the j if and only if I and j are congruent mod n. So now let's just zoom out for a second, literally, but also figuratively, and just think about how this whole thing worked here. I want to go back and think about that list of elements that I wrote down at the beginning of this video, the one that you see over here, the list of all the powers of a. Well, this one only went from a to the 0 through a to the 9th, but you could probably imagine it extending infinitely in each direction. So all the positive powers of a over here, all the negative powers over here. So what I want to convey in this video is that this is actually not quite the right image when a has finite order. The image that we really should have, well, in the case of the order being 5, it should be a to the 0, a to the 1, a to the 2, a to the 3, a to the 4, and then by the time we get back to a to the 5th, that's the same thing as a to the 0. So those are really the same thing. So I've got 5 distinct elements in that sequence. And even if I looked at the negative powers of a, I would just end up traversing this circle the other way. A to the negative 1 would be a to the 4th, because 4 and negative 1 are congruent mod 5. And then a inverse squared would be a to the 3rd, and so on. So the entire list really has only 5 different things in it. It's just each is repeated infinitely many times. And in general, if the order of a is n, then this is the picture that I'm going to see. I always have that a to the 0, that's the identity, and then I have a to the 1st, which is just a, and then a squared, a cubed, and this keeps going around. How many times we don't know exactly, but it's going to be n distinct elements in the list, and then after a to the n minus 1, I get back to a to the 0. That's the same thing as a to the n. So I have this cycle of elements, and the cycle has n distinct group elements, and they are exactly the ones that you see here. A to the 0 through a to the n minus 1. And the reason that worked is when we looked at this list, we realized, well, if there's 2 elements in the list that are the same, then I can sort of operate with those 2 elements and get another element which is equal to the identity. And it turns out that element, or that power that's equal to the identity, its exponent has to be a multiple of n, the order of that element, because otherwise we get a contradiction.